Ready, ready for your questions.
Can we look at the example, the exercise set 5.2 at the end of chapter 5?
Absolutely. Let me go to WebAssign and get the ebook up. Do you want to go into WebAssign actually? Or did you want to just go to the ebook?
Um,
Which one is it that you're looking at?
I got to it through the link, through the book link in WebAssign.
Okay, so we're going to go to section 5.2 exercises. And which number are you looking at that you'd like to discuss?
Number 4.
All right. So the ebook, section 5.2, problem number 4. Good. So for each integer greater than or equal to 2, P of n is this formula. It's an interesting one because the upper limit of the sum is not n, it's n minus 1, isn't it?
Yes.
And that does make this one especially interesting. So it's a sum from I equals 1 to n minus 1. You want to finish reading that for me?
Yes. Then I times I plus 1 equals n. Well, it's the numerator n times n minus 1 times n plus 1, and the denominator is 3.
Great. And so for part A, that we are going to write P of 2, and we're going to find out if it's true or not. All right.
Yeah.
So in fact, that's what we're going to do tomorrow. We're going to do some kind of prerequisite skill stuff because I kind of threw us into the deep water yesterday.
Yeah.
So we're gonna put our swimmies on and back up to the shallower water tomorrow. Um, but let's talk about the fact that this predicate statement has a variable in. That's called the argument. And this is a specific value for the argument, namely 2. And when we write P of 2, we basically are saying, okay, instead of an n, we want to put a 2 wherever there is an n in P of n.
Can I ask a question real quick?
I wish you would.
For the for the predicate statement, we have a right-hand side and we have a left-hand side.
D, we do. Because it's an equation, it does have a right-hand side and a left-hand side.
So the left-hand side is written in closed form.
Indeed.
So, okay, I have a question about that, but I just want to and the right-hand side we assume is true.
Well, actually, when we get to the inductive hypothesis, when we're assuming P of K will be that the left-hand side equals the right-hand side, where there's a K everywhere we currently see an N.
This is what's confusing me here.
Uh-huh.
We have I equals 1 summation n minus 1. But then we have a formula, I times I plus 1.
All right, well, why don't we take a look at this? Let's start by looking at P of 2 and maybe look at P of 3 and P of 4 so you can really understand what this is saying.
Okay.
I know. I know. It's one of the it's about as clear as mud until we do it. All right, so P of 2, if we just wrote P of 2, it just means this whole statement, it is an equation, it is a formula, it is a statement. P of 2 would be the sum from I equals 1, I'll put it in red, the 2, to an upper limit of 2 minus 1 of the expression I times I plus 1 is equal to, so what are we doing? We're writing the formula, the statement, the equation, P of 2, okay? The right-hand side of P of 2, well, you tell me. We know it's going to look like a fraction. Tell me what to write.
The numerator would be 2 times 2 minus 1
Exactly.
times 2 plus 1.
Good. I'm just trying to emphasize that we're substituting in a 2 here. Everywhere we see an n in P of n, it is a 2 in P of 2. Does that make sense?
Yeah.
And it does have a left-hand side and a right-hand side. And to check if it's true, we're going to evaluate the left-hand side of P of 2 and see what it turns out to be. And then we'll turn around and we'll evaluate the right-hand side and see what it evaluates to. If they turn out to equal the same value, then the left-hand side is equal to the right-hand side, and we can be confident to say, hey, P of 2 must be true. So let's take a look at this left-hand side. It's really the sum from I equals 1 to, well, what is 2 minus 1?
It would be 1.
That's right. So it's this, we read this, the sum from I equals 1 to 1 of I times the quantity I plus 1. So we're simply saying, if we wrote this in expanded form, this is closed form, but we're saying this is just a single term because I starts at 1 and ends at 1. So we're just going to say there's just one term in this sum. It's 1, because we're putting in 1 for I, times 1 plus 1, which of course is 1 times 2, and that is 2. So the left-hand side of P of 2 turns out to be 2. Does that
And
make sense?
the expression that you wrote on the right-hand side of that expression is the expanded form, since we just have 1.
No, actually, it's not. Let's write the expanded form. Let's finish this, and then we're going to write the expanded form of P of n minus 1, okay?
Okay.
I know. Maybe I should have done that first. But let's just, this is not just the first term of this sum.
Oh,
This
okay.
is a formula that should work no matter how many terms there are in this sum.
Oh.
There could be 100 terms. This could go up to 101 minus 1. It could be up to
So
100.
So
Which
when you expand that expression, all of the values that you write out, in this case just the 1, are going to satisfy the right-hand side if it's true?
that's right, the sum of all the values. We're
Oh,
going to look at P of 3 and P of 4 maybe so that we can really see what's going on because it is a little mysterious. Let's just finish P of 2. Let's go ahead and evaluate the right-hand side of P of 2. So it's what? 2 times 1 times 3 over 3. Is that right?
yeah.
And that, of course, is 6 over 3, which is 2.
Ah,
So the left-hand side does equal the right-hand side, and P of 2 holds true.
I see.
Now, even though it didn't ask us to find P of 3, let's do that. In fact, would you like to first, shall we just write this out in expanded form?
Yes, it'll have two terms, right? If we use P of 3, because
That's
1 to
true.
2.
That's right. That's right. In general, it'll have n minus 1 terms. So let's look. The expanded form of the left-hand side of P of n in general. Okay? So let's find that. Well, all right, so we're going to look at the sum from I equals 1 to n minus 1 of this expression I times I plus 1. Okay, so this is the closed form, as you well know. Now let's work on the expanded form, and we'll just write as many terms as we need to really see what's going on. I'm going to slide this up because we're just looking at the left-hand side. All right, so when we plug in a 1 for the I, it'll be 1 times 1 plus 1. Okay, so that's the term that we might call A1,
Okay.
right? All right, what would A2 look like?
2 plus 2 plus 1.
Okay, is that what you meant? 2 times 2 plus
Yeah,
1?
yeah, yeah. I'm sorry.
The other plus. Let's write one more, and then we'll do a dot, 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 and then we'll write A sub n minus 1, because that'll be the last one. So what is A sub 3 going to look like?
Plus 3 times 3 plus 1.
Great.
I had a question.
Uh-huh.
At some point in
I'm
that,
going to run out of room. Uh-huh.
at some point in that, I think it's called an ellipsis, the three dots.
Uh-huh.
At some point, it becomes n, and then it becomes n minus 1, and we're finished.
The, okay. Yeah, we imagine going up to some value n, and when we
Oh,
do, the value we're plugging in for I will actually be n minus 1.
okay. See, that's confusing me because so
Uh-huh.
if this were p of 5, for example, then
Yeah.
n would be the 5.
Uh-huh. And it would
So
actually be 4 terms.
I okay. Yeah, that has been throwing me off.
And it
So
should
the
do. It's a little confusing, which is one of the reasons why we force ourselves. It's kind of like eating our vegetables, you know. We force
Mhm.
ourselves to look at it and figure out, well, what happens if that upper limit of the sum isn't just plain old n? You know, what happens when things are quote unquote more interesting,
uh
right? Because sometimes that's the deal. And the reason for that is that the expression on the right-hand side of P of n, you know, if this really works, that the relationship between this upper limit, n minus 1, and this formula is such that you really need the n minus 1 here, you need this middle factor here.
mhm.
If we insisted on putting an n here, then this numerator would have to look like n plus 1 times n. Let's see, n plus 1, this would have to be one bigger. This would be n, and this would have to be n plus 2. And that's really kind of unwieldy. So it's a choice between making something a little more complicated just in one spot. In other words, the upper limit of the sum needs to be n minus 1, or insisting that we have an n here and then having to adjust what's happening here accordingly. It's called a change of indexing. And um, so you know, it's just a choice, but it's a good choice because this is significantly less complicated than maybe it would look if we insisted on putting an in here. All right, since we see this expression here, let's go on. What A2 was I was when I is
It
when
was 2 times 2 plus 1.
yeah. And let's just make a little note here. This is actually that's why it starts when I is 2. This is when I is 2. This is when I is 3, right? A sub 3 is what we get when we put in, you know, when I
Oh,
has the value 4.
oh,
See
I
what I
see.
mean? See it?
So that's the indexing that you're doing, which
Uh-huh.
has
Because
to match
because it
that.
says it starts with n greater than or equal to 2. So
Oh,
n starts at 2. So that means you know, this value, the lowest it could be would be 2. Hang on, this isn't right. Sorry. This is not right. Yeah, when I is 1, okay, yeah. The lowest n can be is 2 because when I is 1, yes, this is a sub 1. When I'm sorry, I is 2, you put in 2 for I. When I is 3, we put in 3 for I. But the largest that we let I be is n minus 1. We don't let it go all the way up to n.
Oh,
So, we start with I equal 1, plus, then I is 2, plus, then I is 3, keep on going, and the top value, the upper limit of I is n minus 1. That's all that means. See,
oh,
see, oh, yeah, we're not going. So when I is n minus 1 and we plug that in for I here, we get n minus 1 times n minus 1 plus 1, which of course is just n.
mm,
All right, so shall we look at P of 3 just to make sure we really, or P of 4? Maybe we can look at P of 4, just so
okay.
we understand what's really going on here. Hey, Sunita, I'm glad you're here.
Hi, thank you.
We're looking in the eBook in
Yeah.
section 5.2 at problem number 4. Let's find P of 4. All right, so we're going to put in 4 for n, because that's what it means. So it's the sum from I equals 1 to 4 minus 1 of I times I plus 1 equals, now what would be on the right-hand side of P of 4?
1 times, oh, 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 oh. 4 times 4 minus 1 times 4 plus 1 divided by 3.
All right, let's check and see if that makes sense. Let's evaluate the left-hand side of P of 4. Okay. All right, so we're going to start and look at this. So I'm going to go ahead and write it one more time. I equals 1 to 4 minus 1 of I times I plus 1. But that's really the sum from I equals 1 to 3 of I times I plus 1. All right, so let's expand that out.
Okay, so that's A1 is 1 times 1 plus 1.
Good.
A2 is, and yeah, it's all added together. A2 is 2 times 2 plus 1.
Yep.
And A3 is our limit is 3 times 3 plus 1.
So let's figure out what that is. It's 1 times 2 plus 2 times 3 plus 3 times 4. So it's what, 2 plus
19, I
6
think.
plus 12. And
20.
that's 20, isn't it?
Yep.
All right. Now, let's evaluate the right-hand side of P of 4. And that's this side, where we put in, 4 everywhere we used to see an n. So we've got 4 times 4 minus 1 times 4 plus 1, whole thing over 3. Let's see what that turns out to be. 4 times 4 times 5 over,
Hmm.
something's wrong.
Shouldn't it be 3? 4 times 3 times 5?
Thank you. I was like, we've got to have a 3 to cancel because we need to get a whole number because sums of integers are integers. Thank you. She got a PhD and she still can't subtract 1 from 4. Okay. And so that is 4 times 5, right? And that's 20.
Oh,
So it certainly works, when we're looking at the sum of 3 terms, from I equals 1 to 3. All right, it's my mother-in-law. All right, so
can we look at something a little more abstract, like you had P of K?
yeah, let's do that. Let's find P of K. Let's find and expand P of K. All right, so we need to see P of n to do this. So there's P of n. So P of k looks just like P of n.
So we're given P of n, and then we work with that.
Yeah, P of n is a statement we're trying to prove. We're not given it in the sense that we don't know it's true. We're proving it's true.
Oh,
Like it's a conjecture that this is true for all integers n greater than or equal to 2. We will prove that by doing two things. The first thing that we would do is show that it's true at that bottom level value for n. In other words,
oh,
we showed that P of 2 is true. That gets us on the bottom step of our staircase to heaven, so to speak. The next part of a proof by induction is to establish that if P of k is true, then P of k plus 1 is true. It
that's
start.
the
Mhm.
oh,
Go ahead.
that's the inductive hypothesis.
Yeah, the inductive hypothesis would be to assume that we are standing on step k. So the inductive hypothesis would be to assume P of k is true. The inductive step is to then show P of k plus 1 follows.
How does P of k relate to P of n?
P of k is a particular but unknown statement. In other words, look at k. All we know about k is that it's at least as big as 2. It is some particular but arbitrary integer. For
Oh,
example, it could be 2. It could be 100. P of n represents any one of an infinite number of statements. P of k is supposed to represent an unknown but particular, an arbitrary but particular one of those.
I get confused because we switch variables so much.
Well, yeah, we do. We need to be able to express this predicate. This is a predicate statement. It involves an integer n, involves a variable n. So remember, predicate statements become statements when we insert particular values for the variables.
Oh
Well, this
yeah.
is a predicate statement. And what we're trying to do is prove that no matter what value n we substitute for this predicate variable, as long as n is an integer greater than or equal to 2, we'd like to show that this will always hold true. That no matter how big and long this sum is, if n is 100 and this is the sum of 99 terms, that sum will equal what we get when we plug in 100 here, here, and here.
Oh,
You see, we're trying to prove an infinite number of statements with a single argument, with one proof. It's kind of cool that we're actually proving an infinite number of statements with just a single proof. So the idea is, to show that we're standing, on the bottom step, that we're standing here. So we got that. We're standing at the bottom of the staircase. Now, what we're getting ready to do, we'd like to be able to climb. We'd like to be able to climb up the staircase forever. Well, when we perform the work that proves the inductive step of the principle of mathematical induction hypothesis, we assume we're standing on step K. That'll be our inductive hypothesis. We don't know what K is, but it's some particular step. It might be the bottom step, it might be way up here, but the point is these dot, dot, dots say, we don't know which step this is, but it's one of them. And we assume we're standing on some step in this staircase, and then our wish is to prove that we will be able to step up to the next step by proving that P is also true at the next integer value. So think of K as an unknown but particular integer value where it's at least as big as 2. we have to let it equal 2 because if we're standing on this bottom step, P of 2, we need to be able to get off of it to the P of 3. So
Mm.
when we assume that we're standing on step K and then prove that we can then step up to step K plus 1, as long as we let K start down at the bottom, that means we can get off the bottom step and start climbing and just keep on climbing because whatever step we're on, we've proved we can step up to the next step.
I see.
Right. So, P of K would be the sum from I equals 1 to K minus 1 of this same expression, I times I plus 1. And the claim is, of course, that it equals K times K minus, oops, I'm looking at the P of 4 to read it. K minus 1 times K plus 1 over 3. That is what we would assume. So if we're going to expand it, this left-hand side, it's 1 times 1 plus 1 plus 2 times 2 plus 1 plus keep on going to the top value, which is K minus 1. So it's K minus 1 times K minus 1 plus 1. That's the expanded form, where this is A1, this is A2, and this is A, so K minus 1, which we get by plugging in K to this upper value. So shall we finish the proof? Shall we go ahead and work the inductive step?
Yeah.
So let's write P of K plus 1.
Well, so are we done with P of K? We set it to equal K times K minus 1, K plus 1 over 3. So that's it?
Well, yes, we would say a few words. We would say, assume that P of K is true. This is our inductive hypothesis. We need to assume we're standing on step K. We're going to get more formal tomorrow. But you assume that you're standing on step K. What does that mean? It means assume that P of K is true. This is P of K. This is just a little extra, just to kind of, this is an aside. You don't have to do this to work the problem. It's just good to see what this actually means. We're expanding. You're taking a microscope and looking at that. All right, so we're looking at P of K. Let's go ahead and write P of K plus 1. Let's make sure we can at least know what we wish, because if we don't know what we wish, there's no way we can prove it. Let's write P of K plus 1.
Would the subtext for the summation be I equals 1 summation K plus 1 minus 1? No, I don't think so.
It would be.
Because we're just substituting all K values become K plus 1.
Exactly. So it's K plus 1 minus 1 as our upper limit of our sum of I times I plus 1. Yeah, it makes my sum look funny. Now, what's the right-hand side? Oh, we're writing P of K plus 1. My bad.
The right-hand
Yeah.
side is K plus 1
And we have to use
times,
parentheses.
oh yeah, times K plus 1 minus 1 times K plus 1 plus 1
Good.
over 3.
Fantastic. And we're gonna go ahead and simplify it a little bit, just so we get a better handle on what we're really looking at. Okay. So what is the left-hand side? What happens when we simplify that?
It becomes I equals 1 summation K, because we
Great.
just removed the K's.
Uh-huh.
I times I plus times I plus 1
Great.
equals, and this is K plus, well, this is times k, because the ones cancel out, times k plus 2 over 3.
Yep, that's P of k plus 1. And that would be what we would wish to show. This is our wish. That's why I put my little dreamy wish cloud around it, because it's really easy to confuse what we have in our hand, which is P of k, with what we wish to prove in the inductive step. We assume this, and then we wish to prove the next step up. And the next step up for this particular formula looks like this. So when we write the actual formal proof, we'd say proof by the principle of mathematical induction. And we would just say, hey, let's let P of n be the statement that the sum from I equals 1 to n minus 1 of I times I plus 1 is n times n minus 1 times n plus 1 over 3. And we're going to prove it for n greater than or equal to 2. That's what we're told to do. So in our basis step, we let our n naught value, start at that lowest level value. We have to be told what that is. Let n naught equal 2. What do we wish? We wish to show P of 2 is true. And so you can, write, the left-hand side of P of 2 is, and then the right-hand side, I'm not going to write it all again because we already have, of P of 2 is blah, 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 and then we realize, oh, okay, so the left-hand side equals the right-hand side, which means P of 2 is going to be true, right? We've already done that, but you would just rewrite it here in the formal proof as the basis step. Does that make sense?
Yes.
Like we already did that work here, right? You could write P of 2 if you want, but usually we just go ahead and just look at the left-hand side and the right-hand side separately.
For I times I plus 1, that would be a sequence like we've been identifying?
Uh-huh. It
Okay.
sure is. So yeah, this could be the formula. If I gave you a sequence, right, that started out 1 times 2 plus 2 times 3 plus 3 times 4 plus what would the next term look like if we were going further?
4 times 5?
Plus dot dot dot.
Oh,
Then yeah, no, you did it right. I was just going to finish your yeah, plus 4 times 5 plus, and then just whatever, you keep going. If I gave you that, then you would give me the formula for a sub I. You would say, oh, a sub 1 is 1 times 2. A sub 2 is 2 times 3. Oh, a sub 3 is 3 times 4. Sure looks like the term a sub I is I times I plus 1. See what I mean?
I see. It's a lot going on here.
There sure is. There sure is. And that's why we're going to take our time and we're going to spend several more lectures on mathematical induction. We've just started to think about it. The thing about this particular proof is, okay, so you know what to fill in here. We did this earlier. I'm not going to rewrite it. But then just to show you what the complete proof would look like, then we're going to work on the induction step. And in the induction step, we tell our reader we're going to play with a k, so we tell the reader what k is. Let k greater than or equal to 2 be an integer. It's some integer, some particular but arbitrary integer. In fact, I used to make students say particular but arbitrary. I've given that up, but it really is some particular but arbitrary integer. Because otherwise it kind of sounds like we're just assuming that P of k is true for all integers k. We're not really. That might have confused you a little bit. Assume P of k is true, i.e., we're going to assume that we have that the sum from I equals 1 to k minus 1 of that expression for, the ith term is equal to k times k minus 1 times k plus 1 whole thing over 3. That is our inductive hypothesis. This is where we assume we're standing on the kth step of that staircase. So I like to put a little box around it to remind myself, this is what I've got in my hand. This is our proof money. This is like our money in the bank. And we get to spend that. All right, so what do we wish? Well, we wish to show we can step up a step. So proof continued. I change from black to blue. Is this black or blue? I think that's black. That's hard to tell. Proof continued. Okay, so what do we wish to show? We wish to show P evaluated at k plus 1 is true. All right, let's write down what P of k plus 1 really is. What is it we're really trying to prove? Okay, so instead of a k, we're going to have a k plus 1. So it's k plus 1 minus 1 for our upper limit of our sum. And then everywhere there's a k, we're now going to have a k plus 1. And I'm going to even, we can leave it like that, but it might be a little helpful just to realize we're really looking at the sum from I equals 1 to k of I times I plus 1 equals k plus 1 times k plus 2 over 3. And that's our wish. We wish to prove that that's true. And then comes the fun part. We cannot start with the equation we wish to establish. That's a huge no-no. But we can work on the left side for a while till we get tired of doing that. Then we can work on the right hand for a while, right-hand side for a while, and show that they both turn out to be the same thing. And that means, oh, if this is equal to C and this is equal to C, then these two must be equal because they turn into the same, expression. Or I like to try to do it sort of in one fell swoop. I like to just start with the left-hand side of P of k plus 1 and work on it until it changes into the right-hand side. That's another approach. So, but this is our wish, okay? But this is what we have in our hand. This is called our inductive hypothesis. So there's a trick, breaking off the k plus first term of a sum, or breaking off the kth term in this case. So this is a very confusing one that you've picked. Starting with, because of this interesting upper limit, starting with the left-hand side of P of k plus 1. Let's just start with this and see if we can turn it into that. It's the sum from I equals 1 to k of I times I plus 1. But isn't that the same thing as the sum from I equals 1 to k minus 1 of I times I plus 1 plus the sum starting right after that, which is k, because the next integer after k minus 1 is k, to k of I times I plus 1. Isn't this sum expressible like this?
Yeah, I see it.
We've broken off the last term, kind of split it apart, But the reason we did it is because we know something about the sum from I equals 1 to k minus 1 of I times I plus 1. We know something about this.
That's P of K.
It's the left-hand side of P of k.
Ah,
And we have assumed that the left-hand side is equal to the right-hand side. That is our money in the bank. We know these two are actually equal. So when we see, that's the reason we break off the last term so that we can see the sum of all the terms right before that. All of them up to right before that, because we can make a substitution now. And when we do this step of making this substitution using our inductive hypothesis, we tell our reader, and I don't care what level you're at, no matter how advanced in mathematics you are working, you always tell your reader when you actually use the inductive hypothesis, or you can just say by induction. But the point is, what happens from this step to this step can be completely mysterious if you don't remind the reader, oh, I'm using my inductive hypothesis that says that this sum looks like k times k minus 1 times k plus 1 over 3. And then we still can write this. This is, of course, we can just evaluate this, or you can write it one more time, but this is just a single term where I is taking on the value k. So we can just plug in k
okay.
everywhere we see an I. And we're a lot closer to what we wish to get. We started with this left-hand side. We're trying to get that. This doesn't look anything like that, but breaking off that last term in the sum and making this inductive substitution, what we are looking at right now is a lot closer to this right-hand side that we're shooting for than we were when we were sitting with this. And now it's just a matter of doing some algebra. Do you see what I'm saying? You can kind of check on your progress. You can say, okay, I've got this. I can break off the last term. I can use induction and substitute in using my proof money, but I still have to do some work to get to here. But at least we know what we're shooting for. So let's compare and contrast. This is what we've got. We've got something plus something. We want just a single quotient, just a single fraction with a product up top and a 3 on the bottom. Well, we're not that far away from there. I can slide this up now because we've used our inductive hypothesis.
We need to raise the second term to
Yeah,
by 3 because we need a common denominator.
we need a common denominator of 3, and that gets us even closer to our wish. This is already over 3. So we have to multiply this times 3 so that we can put it over 3. I mean, we're basically just multiplying this by 1, 3 over, our favorite version of 1 for the moment, which turns out to be 3 over 3. And now we're even closer to getting this. At least now we've got a single quotient with a 3 on the bottom, but we have a sum instead of a product. We want a product of 3 factors. Well, we have a sum of 2 terms. They're both products, but we want to just get a product. So what is the trick for getting a product from a sum? There is a trick.
Hmm.
It's called factoring.
Oh, right. But the numerators, the two terms don't have, well, they have k's in common, but they don't have the 3's. Okay, all right. Makes sense.
Yeah, I'm a little worried. But let's just play this out. Let's look at both of these terms, this one, and let's ask, what are the common factors to both of these that we could factor out? We can't factor out a 3 because we don't have a 3 here, but what could we factor out from both of these?
A's,
Yeah, we can pull out a K because there's a K here and there's a K there as a factor. Good. Anything else?
Those ones, we could probably pull out negative ones, or I don't know
We
exactly.
got to pull out a whole factor, something that the
Oh, oh,
thing.
K plus one.
Yeah, we can factor out a K plus one from here and from here. Great. That's it. Now let's look at what's left. When we factor out K times K plus one from this first term, what's left over?
K minus one.
Okay. And when we factor out K times K plus one from this product,
Ah,
what's left?
we have three left over. Plus three. Hmm.
I'm not worried anymore because that last factor can be simplified. What does it become?
K plus two. Hmm. Which
And
is
that,
what we needed.
yeah, and we can rearrange it so it looks like, exactly the way it needs to look. And then you can even go one more step. This is, K plus one times K plus one minus one plus one over three, which is the right-hand side of P of K plus one. So let's just regroup. What the heck just happened?
Yeah.
We started with the left-hand side of P of K plus one, right? We figured out what P of K plus one looks like, and we wanted to prove that's true. We started with the left-hand side. We broke off the last term of the sum so we could use our inductive hypothesis, which told us, hey, that is equal to that. That's our P of K. We used that. And we evaluated that broken off term. And then we just kept saying, ooh, we need to get this. What do we need to do to get closer and closer and closer to that? And we finally got it. So we started with the left-hand side of P of K plus one, and we showed it really does equal the right-hand side.
Wow.
So then we can just wrap it up. We got just a couple more things. Let's go on and finish it. So the left-hand side equals the right-hand side in P of K plus one. And we have shown that if we have P of K, then we can get P of K plus one. And then the last step is to invoke the PMI. And we haven't talked about that. We're going to talk more sort of about the principle of mathematical induction in general tomorrow, just to kick off our discussion. We're going to dig back in to looking at the definition, but the PMI is not something we prove. It's something that we use. It's a principle. We don't prove principles. We assume they're true. They're taken to be so obvious as to be self-evident. I'll give you a principle that you're very familiar with. I'm sure you've heard this. 2 points determines a line.
Yes.
And we don't ever prove that. We take it as what's called an axiom or a principle. We assume that that's true and we go from there. Well, the principle of mathematical induction says if you can stand on the bottom step and if you can show that from the kth step you can step up to the k plus first step, then the conclusion of the PMI is that we can say the statement P of n, I'm not going to rewrite it all here, but is true no matter how large n gets. So for all integers n greater than or equal to the bottom level, which was our n naught, and I want to actually put in that value. It was 2. That was our n naught. You always put n naught here. So that's what the PMI says. It says if you can prove the basis and you can prove the inductive step, then the PMI for free, the principle of mathematical induction for free, tells you, hey, that statement is true forever after. It's true no matter how large n
Wow.
gets. So we just invoke it. We're not proving it. We're actually using it. And if you go back And look, we'll have, the new notes for tomorrow are up. And the first page of the notes gives a little cleaner, like I said, I threw us into the deep water yesterday, but tomorrow we'll clean it up. I rewrote the principle one more time and sort of broke it up. It's an if-then statement. It says if you can prove 1 and 2, or if you know that 1 is true and 2 is true, those two little parts of the big if statement, then you get to say that your statement is true forever after. So, we're not proving the principle of mathematical induction. We're using it by showing that the hypothesis of the principle holds. That is our work, is to show that the hypothesis of the principle is true, and we get the conclusion for free, which is what we want. We want to show that that's true for every integer n, no matter how large n gets, where n starts at the value little n naught, whatever that is, 1 or 2 or 3 or 0, whatever it starts at. I gave you more than you bargained for there. Sunita, it's your turn. I know it's already 9, but maybe you're looking at some of the measure 2 material from section 5.1. Maybe you're looking at that worksheet or something completely different. Do you have a particular question or two that we could address now? I don't mind staying later since I've.
You asking for me?
Yes. Do you have some questions?
No, I'm working on my measure to material, so maybe yeah.
So shall we look at the measure 2 material together, maybe?
Let me.
Here, I'll bring it up. I'll share my screen.
Not not this one. I have done this one, so let's go down. I think yeah. These are I have to do it.
Using the formula?
Yes.
Okay. So, have you tried 5A?
It's like, so the n is 600, right? So using the
Yes. Yes.
and I equal 1 and I equal 1. So yeah,
That one's pretty easy, isn't it?
yeah.
So our formula is that the sum from I equals 1 to n of I is n times n plus 1 over 2. That's our formula, right? In other words, 1 plus 2 plus dot 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 plus n is given by this formula. You can write it either expanded or closed form, right?
Yeah, I can do it. This one, yeah.
So you can do A. A is easy, right? Because it's just 1 plus 2 plus 3 plus dot 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 plus 600. So here, n is 600. We just plug in 600 here, and then What about B?
I think B also, yeah, it's like
You can do B? Great. What about C?
C. It's so pretty. It's like there is like a common difference. It's like 1. It's a one.
Okay, let's look at C. What does it start? C, C is easy, right? You just pull out a 4. But C starts what, at 900? Or does it?
Yes, 900, 901, 902, something like this. Yeah,
How far does it go?
like T and then 1800, something.
All right, so the thing to realize about this is we're not starting at 1, but isn't it true that if we did start at 1 and went all the way up to 1800, but then subtracted the first 899 terms in the sum? Wouldn't that actually equal the sum we're looking for? That's the trick there. Because if you start at 1 and go all the way to 1800, well, that's more than we want. We'll take away the first terms, that we don't want. The first terms of this sum are from 1 to 899. That will be, so it's a difference. It's a difference formula from I equals 1 to 1800 of I minus the sum of the ones we want to throw away. Starts at 1 but goes up to 899 of I. That will give us the sum from I equals 900 to 1800 of I. It'll be what we get if we take the whole big sum all the way up, starting at 1, and subtract the first 899. So you just use the formula twice, once for this and once for that.
Okay.
Does that make sense?
Yes. Yes.
Those are our 3 tricks. Well, 2 tricks. One trick is to factor out, a common factor. The other trick is to use subtraction. So if I gave you another one and I started at, 505 plus 510 plus 515 plus keep on going up to say 5,000, this problem combines both tricks where you factor out something and then use a difference. Okay.
On the question C, you have the 900 plus 901 plus 902. It's 1 plus 2 plus 3.
Yeah.
Right?
Yeah. If you right. Yeah. I mean, we had to subtract, right, to get the one that started at 900. Where will this one start if you do a factorization? What would you factor out of everything?
It's 505 and
Do you see you can take a 5 out? Each of these is divisible by 5. You see, what you do is just look at the jump that's being taken to get between terms. How much are we adding to get from here to the next one? See, the jump is a jump of size 5.
15. It's 5,
But what we need is a jump of size 1. Our formula says we have to have a common difference of the size 1. You see how these are all 1 apart? We can use the formula with our extra little trick of subtracting.
Yeah.
See here, we didn't need to do anything. These are all 1 apart,
Yes.
and it just started at 1 and ended at n. So there was no big deal here. The second one, B, I think it was 4 plus 8 plus 12 plus ... up to, I don't know, something like 4,000 maybe. Well, we need to see, these are jumps of size 4. So you pull out the 4. And now we can use the formula because this starts at 1 and ends at n equal 1,000. We just have to be sure to multiply by 4 at the end.
Mm-hmm.
This one, it's jumps of size 1. That's not the problem. The jumps are the right size, but it didn't start at 1. But if we do this trick, both of these start at 1 and have jumps of size 1. So the formula applies. We just use subtraction.
For the D, so we can pull up the pipe out and then go to the 1 plus 2 like that. Or 1.
And now, since this isn't starting at 1, you can use this trick of subtraction applied to this one.
Okay.
Take the sum from 1 to 1,000, but subtract the sum of the terms that are missing from 1 to 100.
Mm-hmm.
Does that make sense?
Yes. I'll do it later, that one.
Okay. Were there other, did you look at some of the other ones there?
No.
Have you practiced with N choose R? Here's our formula.
No, I haven't practiced. I just came over only the question number 5. That's it.
Okay. So our quiz tomorrow is going to be on guessing formulas. Okay, so you said you've done these?
Mm-hmm.
Great. That's great. And it's going to be on N choose R. I think that's it. And it's actually going to be an open quiz. People are going to be able to work together on it. I've decided we're going to spend, kind of a 15-minute sort of a group.
I'm in today's class.
Oh,
Yeah,
you're in you're in Wednesday class, right?
so
You
you
had to quit. Were you in class today, Sunita?
yes, I
You were there? Oh, you were working with
Maxine,
y'all were working at the front.
Benz,
You were working at the front, right?
because yes.
Okay. So you had the quiz. Okay. Huh.
It was like quiz 7 for the
Oh, it's
next.
quiz 6.
Yeah,
Quiz 7 is a take-home quiz and it's posted.
yes,
It's 2 induction problems to work on, but
yes.
after today's lecture, you'll probably, did you understand today's lecture?
The lecture, yes, but it's like I need to like more office hour ready.
Okay. So we can have, an extra office hour maybe, but you work all the time, right?
I can be like I can I do have time for Friday.
Friday? Okay. Friday morning, I have a meeting in Zoom from 11 to 12. Can you do an office hour at 10 on Friday?
In the morning.
Yes,
I can do.
you can do? Hello?
Yes, I can do it.
All right, we can have an office hour from 10 to 11, but I have to leave. Well, it can be 10 to 10:55. I have to leave at 10:55 because I have to be in another meeting at 11, and my boss is in that meeting, so I don't want to be late to that next meeting. But yeah, 10 a.m.
Yes, I'm ready.
Okay, I will send around an announcement and so that everybody that wants can come. Is that okay with you? But we'll talk about induction. Is that okay, or do you need a private office hour?
No, no, that's okay. I'm okay with that.
All right, we'll work on induction.
Okay.
Okay,
Thank you.
you're welcome. Nora, I hope that this helped you tonight. Thanks for hanging out.
Thank you, Professor. I need to look into the Measure 2 material. And when is it due?
I think the due by date is beginning of next week, Monday
All
or
right.
Tuesday, depending upon which class you're in. For you, it'd be Tuesday. But
Well, I'll do, it'll
Mhm,
help me prepare for the quiz on Tuesday.
it will. Well, the quiz is tomorrow.
Yeah, oh, yeah, right. No
And the
problem.
take-home
I'll get
quiz,
it.
the take-home quiz is 2 induction proofs. But
Okay.
you'll be more comfortable with the induction proofs after we have lecture tomorrow.
Okay.
Plus, we did a really hard one tonight because it's actually really challenging when the upper limit is weird. Like it makes it a little not, it's like it's hard enough when the upper limit is just in. When the upper limit is something that's not in, it makes it even more challenging.
This was really helpful, though. I thank you for this.
You're very welcome. Thanks for coming. Thanks for playing. All right, I'll get these notes posted and the video up. And I'll
All
send
right.
out an announcement. We'll have an extra office hour on Friday morning.
Thank you. Thank you so much and have a good
Thank
night.
you, Professor. Have a good evening.
Thank you. Bye.
Bye.